So I'm going to talk about something quite different, and a lot of it's to do with interdisciplinary research, which is something that Alex was mentioning earlier. And I put the acknowledgements at the start because the type of work that I'm going to talk about for the next 10 minutes or so couldn't happen unless we worked not only across departments but also across divisions. And so in blue here you have some of the clinical collaborators with whom I work, and in green some of the research assistants. This is roughly half my research team because we do other things when we're not looking at this problem of trying to identify patient deterioration in hospital. If I'd been asked to give this talk 5 years ago, I would have talked to you about engine deterioration. I worked with Rolls Royce for 15 years, worked on the Trent engines from the Trent 500 to the Trent 900 and the Trent 1000. As I'm sure most of you know, the Trent 900 is the engine of choice for the Airbus A380, and the Trent 1000 is the engine of choice for the Boeing 787. Rolls-Royce really doesn't mind who wins in the war between Airbus and Boeing because it supplies engines to both. And one of the things that we did, we analysed the first data of the first flight of the Trent 900. This is actually a flight with the Rolls-Royce test engineers inside an Airbus A380. And of course, when they're doing test flights, they remove all the seats and put a lot of instrumentation there and so on. We used to be allowed to go up in the flights, but there was an untoward event, shall we say, about 10 years ago, an Italian team, and so now they don't allow academic researchers to go up in the planes with them. But nevertheless, we analysed the first data that came back ever from the Trent 900 in flight. If I move on to the next slide. Some of you may know that the business model has changed in Rolls-Royce in the last 10-15 years, in that they don't make any money on the engines. In fact, they lose money every time they sell an engine. They make money on the total care package that they sell with it, which ensures that the planes are kept up in the air 99.9% of the time. Because of course, if a flight from Rome to Frankfurt is delayed because of an engine problem, it's the flight from Frankfurt back to Heathrow and then on to Madrid, etc. That'll also be delayed. Airlines have to compensate passengers, and in the end, it's actually the engine manufacturers that carry the buck. And therefore, they now have total care packages, and some of the software they use in their Derby headquarters to review the data was developed within my group, and they proudly announce that every day they monitor 25,000 hours of engine data in real time, which I'm sure you're very pleased about as you fly around the world. Now, if we, having moved to the Institute of Biomedical Engineering 5 years ago, the application of these kind of signal processing techniques I'm going to mention briefly moved from jet engines to patients, although we're working both in parallel. Where do you have a total care package in the healthcare world? Well, intensive care unit. So here's a typical intensive care unit bed up at the John Ratcliffe here, and you have all sorts of support for the major organs, and then one thing that you don't have to do for jet engines is also emotional support for human beings. However, what I'm going to talk about in the next few minutes is not the intensive care unit, because in the intensive care unit is one nurse per patient. It's what happens below the intensive care unit. So intensive care unit is level 3 in terms of NHS levels. The level below is level 2, and the general ward is level 1. Level 2 is, for example, a step-down unit or high dependency unit or coronary care unit or the emergency department. Level 1, the general ward. And about 50,000 people who have adverse events in hospital every year who shouldn't. Some people end up as an unplanned mission to intensive care. And if that is the case, as opposed to a planned admission after major surgery, your risk of dying is 2.5 times that of dying after major surgery, so of the order of 50%. And likewise, if you have a cardiac arrest, when the heart stops beating in hospital, and there are about 25,000 such occurrences in the UK every year, your chance of surviving the DGH and walking through the front door, about 1 in 20, at the JR is probably 1 in 4. And the problem is all of these are avoidable potentially because there are abnormalities in the physiology denoted by the vital signs, the heart rate, the respiratory rate, the oxygen levels, the blood pressure, temperature level, consciousness, up to 8 hours before, reported in the literature in 50% of the time. Now actually what we have shown is that 50% is probably 90% rather than 50%. And if you are able to track the vital signs, you should be able to infer the status of the patient. The problem is, as with many signal processing problems, whether it's jet engine data or data recorded from patients, the signal is buried in the noise. And the trick for us is to try and find the signal of interest in order to identify deterioration early, because as with everything in medicine, early detection improves the outcomes of the patient. And so working in high dependency unit or the step down unit, one below the intensive care, from the bedside monitors, we've developed very similar techniques that we use with jet engines to fuse all the data. Here the 5 vital signs, building multivariate models, and you'll be glad I've removed all the equations from this talk. And the idea is to build a model of what physiological normality would be, so that when the patient becomes abnormal, the system, the data fusion system, can alert as early as possible. And in a 2D representation here with just 2 of them, the breathing rate and the heart rate, you can see that the normal behavior is within this kind of envelope, so average heart rate and average breathing rates, and you can either have a deterioration, one vital signs changes suddenly, here the patient becomes tachyapneic, with very high breathing rates, or 2 move together, slightly rarer, but often a precursor to major events. So we built this data fusion system, originally tried it in John Radcliffe, but one of the problems working healthcare is that it's dominated by the US and their reimbursement system. It has to be, any system has to be approved by the Food and Drugs Administration, the FDA, and if you really want it done properly, you have to do a clinical trial in the US. We did a clinical trial in Pittsburgh, started with retrospective analysis where we showed the data fusion system alerted on average 6 hours before the crash team was called, and remember, early detection improves outcomes, and then we use it prospectively where nursing staff were mandated to respond by the alerts of the team, attempt to deal with the patient, stabilize him or her, and not call the crash team if at all possible. And what we observe is dramatic reduction number of patients becoming critically unstable. There were 6 unexpected deaths when we'd done the retrospective analysis in the observation phase out of 320 patients, none in the intervention phase, no fatal unexpected cardiac arrest in 18 months of using the system, whereas there's about 2 a month in the 2 years previously, so about 50 in the previous 18 months. And that gave us the data to make the system FDA approved, and it is now used in quite a few US and some UK hospitals, with 137 software licenses having been sold, as I say, mostly in the US. Now, one other thing to say, that's the high dependency unit, the emergency department, A&E, coronary care unit, and so on. That's 10% of the patients in hospital. 90% of the patients are sitting on a hospital ward here. What happens is the nurse comes round, takes your blood pressure, measures uses an instrument on the trolley that she brings with her to measure the heart rate and oxygen saturation as well, uses a tympanic thermometer, and also counts your chest wall movements for your respiratory rate and assesses your consciousness according to the Glasgow Coma Scale. What they then have is observation charts, and they have to convert the numbers, vital signs, into an early warning score. The higher the number, the more abnormal you are. To cut a long story short, and not to delay PIMS and other fizzy drinks too much, we redesigned the system based again on statistical analysis of the data, which is really bringing the methods of the physical sciences and mathematical sciences to the clinical environment, working with our clinical colleagues, and produce an evidence-based early warning score based on about 60,000 hours of trial data we'd collected in the previous decade, and introduced this about 18 months ago throughout the Oxford University Hospitals Trust. So every hospital, acute hospital in Oxfordshire, thousands of patients every day, is monitored using these charts. And the first 12 months after the introduction of the charts, we've had a 10% reduction in cardiac arrest already, which is one of the indicators that hospitals have to report. So we're moving to the electronic version of this as we speak, and that's the meeting I was at before coming here. So that's the kind of work that we're doing today to improve patient outcomes both in level 2 and level 1 wards in the NHS as a collaboration with engineers and clinicians. For the last 3 minutes, and it'll be short because I don't have the video to show you, a quick insight on the future. As I said, 90% of patients are on general ward, and they spend 80 to 90% of their time in bed over 24 hours, or close to the bed reading a newspaper, for example. We can't, for all patients, stick wearable sensors on them. The technology is simply not ready. It's probably a couple of decades away. But what we can do, and some US hospitals have started doing, because there are individual rooms, is actually to have a webcam in the room here. You can just see there. And what we are going to be doing with this webcam, and there are other teams in the world who've started to do this, although I think we're still the only ones who've published clinical data, is actually to measure the reflectance from the face with a webcam to measure heart rate, breathing rate, and oxygen levels. So you've got the red, green and blue data stream from your webcam, and we use autoregressive models, which are mathematical models, as I'm sure a lot of you will know about them, with interesting properties. They're able to track any dominant frequencies in the signal, which we'd expect to be the cardiac rate and the respiratory rate. The angle of the pole in the model tells you what that frequency is, and the magnitude of the pole tells you how strong that particular component is. So we've been doing some trials in the Oxford Kidney Unit with the renal physicians, because dialysis patients are quite unstable patients, so they're double monitored. There's a chest band to measure respiratory rate, a blood pressure cuff, a finger probe, and of course our webcam. And if we look at the correlation between the double monitoring and our system, in black you have the reference values, so this is the heart rate of a patient in black. In red, this is over about 10 minutes, the estimates from the camera. You can see we can track the heart rate pretty well. And this patient suffered from sleep apnea, which means cessation of breathing while asleep. And you can see the dips in the breathing rate here from the chest belt while he's asleep, and they're tracked by our respiratory rate estimate from the camera. And at this point, I was going to give you a video demonstration. If anybody wants to come back during their drinks, I can show you the video of this, which is effectively the student working on this. I'll get the computer working again. I'm not going to have a drink till it's working again. So you have the estimates from the camera here, heart rate and breathing rate. He's wearing a finger probe telling what the heart rate is, and there's no proper technology to do breathing rate estimation, and therefore we can't tell what the reference is. So are we cheating? We're not. We've trained our student to breathe at a metronomic rate. And the video would show you the metronome here, and that's where we get the reference from. It's actually set to breathe at a particular rate, and then we can compare the camera values with this. So that's where we are with jet engines. Every day Rolls Royce monitors jet engines, 25,000 hours of engine data in real time, including the A319 who you've read about in the press, except that wasn't Rolls Royce engines, so they haven't got that data. But all the major incidents, like the aircraft that landed short of the runway at Heathrow just before Gordon Brown was about to go off on a tour of the Far East, all of that data is held and reviewed by Rolls Royce. You'll be glad to hear. And what we're doing in the next 5 years, as a collaboration between MPLS and medical sciences, is really to take the John Radcliffe into one of the leading hospitals in the world for patient monitoring. So I haven't talked to you, because I haven't had the time, about what we do in intensive care unit. I haven't talked to you about what we do about home monitoring, but what we're doing in the high dependency unit, as you've seen, is the continuous bedside monitoring. On a general ward, we're introducing the early warning call system electronically. This is a landscape shot from our iPad app. From some selected patients, we are using wearable sensors in the hospital Wi-Fi, and we're also doing, in some clinical areas, real-time monitoring with the webcam. Fusing all of these data, then integrating it with the electronic patient record that gives you the other data, so that we can have early warning of deterioration and improve hospital outcomes. Thank you very much indeed.